Hello everyone. In this video, we will talk about the halting condition of bisection method. So when you use bisection method, you need to do the iteration over and over again. So what are the conditions that may cause the iteration process to halt? There are two conditions. The first one is that FC equal to 0. Remember that we always start from the interval A to B. And then we find the middle point, C, which is A plus B over 2. It's possible that this middle point C happens to be the root. Although it's very unlikely in practice, but it's possible. If that happens, then we can stop the iteration because we have already found the root, which is C. And the second condition is that we halt if the following two conditions are met. Let's call this condition A and condition B. So when both condition A and condition B are satisfied, then we halt. The condition A is that the width of the interval A to B is sufficiently small, which means B minus A is less than a certain value. We call this certain value epsilon step, which is a constant. Remember that when we use the bisection method, we do the iteration over and over again. After each iteration, the width of the interval will shrink by 1/2. So when we do a lot of iterations, the interval will become very small. And let me draw a function just to show you the idea. So if we have xy a function like this from, for example, this is A, this is B, then we find the interval C, right, and remove this 1/2, and then find the interval, middle point, and then remove this 1/2, and then find the middle point, remove this 1/2. So if you do this over and over again, the new interval here to here, so this will be the A, this will be the B, right? So this interval A to B, right, becomes sufficiently small. For example, this A is 1.000345, and this B is equal to 1.000346, right? We know that the root is always inside the interval A to B, then the root will be somewhere between these two values, right? For some applications, we may not need extremely accurate root. So if we say that the root is somewhere between 1.000345 and 1.000346, that's good enough, right? So we can use A or B as a very reasonable evaluation of the root. Then we can stop the iteration. If this is not good enough, you need more digits to have a more accurate root, then you need to continue the iteration. So it really depends on the value of epsilon step. If you need a very accurate root, epsilon step should be very small. And if you don't need a very accurate root, epsilon step can be larger. Okay, so let's see condition B. Condition B is that the function evaluated at one of the endpoints is small enough. So which means the absolute value of FA is small enough. It's less than a constant, which we call epsilon ABS. Or the absolute value of FB is less than a small constant, which we call ABS. Okay, so for this condition, if we call this condition B1, this is the condition B2. So the condition B is that condition B1 or B2 is satisfied. So you don't have to satisfy both of them. You just need to satisfy one of them, right? So for condition 2, right, it includes condition A and condition B. So both of them should be satisfied, A and B. And B is condition B1 or condition B2. right? So this is the second condition. So let me explain why we need this condition B. So for example, at some point when you do the iteration over and over again, right? So this is a function, you have a very small interval, right? A to B. We know that this interval is small enough, then we can use the value of A or B as the approximation of the root. But we still need to evaluate what's the value of FA, and here what's the value of FB, right? If they are exactly the root, they should be, FA or FB should be 0, right? Since they are the approximate value of the root, so they are not there exactly 0, but they should be small enough. For some function, for example, we have function like this, right? They increase very fast around the root. So when you are a little bit off from the root, the value of this FB becomes very large because the function at during this small interval, it increases so fast. So FB is very large. Then it's not safe to say that B is a proximate value of the root, right? So we need to evaluate FA or FB to make sure at least one of them is small enough. Then we can use A or B as the approximation of the root. Okay. So if we halt due to condition 1, then we can say that the middle point C is the root. So if we halt due to condition 2, then we can choose either A or B as the root, depending on which one is more accurate. So if the absolute value of FA is less than the absolute value of FB, we use A as the root. If the absolute value of FA is larger than the absolute value of FB, we use B as the root. Okay. Let's see an example. So this example is actually the same example I showed you in the last video, but this time I add the halting condition. So you can see in the end what's the approximate value of the root. So consider finding the root of fx, which is x squared minus 3, and start with the interval 1 to 2. And we assume that epsilon step is equal to epsilon abs is equal to, both of them are equal to 0.01. So as I showed you in the last video, you can do the iteration over and over again, right? Just follow this table. Assume that you did 1, 2, 3, 4, 5, 6, 7 iteration. And after the 7th iteration, you found that the width of the interval, which is b minus a, is equal to 0.0078, which is less than this epsilon step, right? Then the condition A is satisfied, right? And let's check condition B. So the absolute value of FA is 0.0457, which is larger than the epsilon ABS. So condition B1 doesn't satisfied, right? Isn't satisfied. But FB is equal to 0.0081. So the absolute value of FB is less than epsilon ABS, right? So we can say B2 is satisfied. Remember that B1 and B2, only one of them needs to be satisfied. Then we can say condition B is satisfied, right? Because one of them is satisfied here, we can say condition B is satisfied. So both condition A and condition B is satisfied, then we can halt the iteration process. Okay, so what's the root in the end? you can see that the absolute value of FB is smaller than the absolute value of FA, which means B is a better approximation for the root. Then we choose the value of B, 1.7344, as the root. Okay? So in the next video, I will show you how to implement bisection method in MATLAB for root finding purpose.